Hi guys, welcome to a new video. In this opportunity we are going to solve a problem related with the conservation of energy. The problem says, a light non-stretching cable is wrapped around a solid cylinder with mass m and radius r. The cylinder rotates without friction around a stationary horizontal axis. The free end of the cable is tied to a block of mass m and the block is released from rest at a distance h above the floor. As the block falls, the cable doesn't stretch or slips. Find expressions for the speed of the falling block and the angular speed of the cylinder as the block hits the floor. Well, we have the illustration on this page, and this is the situation before, and this is the situation after. So, in this example, the cable doesn't slip, right? So there is no friction between the cable and the disc. We assume that the cable is massless, so that the forces that it exerts on the cylinder and block are equal. All right? So basically, the forces or the force that the cable is exerting on the mass and on the cylinder are equal, right? So but this happens because the cable is massless and it has no friction with the cylinder. So on this part of the illustration before, the block begins to fall, right? And it starts falling from this distance h. This is the initial position of the block. So on this part we have two energies, the kinetic energy of the system and the potential energy of the system. Okay? We call this kinetic energy, and this is the potential energy. So we will see how we can write these energies for each situation of this problem. We will take the gravitational potential energy U to be 0 when the block is at the floor. So our point of reference is this part, is the floor. So on the floor, right there, the potential energy is going to be 0. All right? Okay. When the block has fallen the distance h right before the block hits the floor, it has a speed b, right? A speed b. So the total energy is going to be the kinetic energy plus the potential energy. So on this part of the problem, we will have the kinetic energy and the potential energy. Okay, guys? All right. So let's do something. Initially, the kinetic energy, if we come back to the situation before, we will have the kinetic energy equal to 0. Okay? Because the system is at rest. All right? At rest. And the potential and we know that the kinetic energy is the energy when the body is moving, okay, with a velocity v. The potential energy, by definition, we know that the energy, if we have this lever right here and the position of the body is h, by definition the potential energy is going to be the mass multiplying the gravity multiplying the position. In this case, the height h. Now, if we go back to the situation after the block falls, we have the energies of the system as well. So, the kinetic energy is going to be the total kinetic energy, because at this point of the problem, the disk is rotating with angular velocity w. All right, and the mass has velocity, linear velocity v. So we have two bodies moving. Then we have the composition of the kinetic energies. Okay, the kinetic energy of the block is going to be by definition 1/2 of the mass multiplying the velocity square plus the kinetic energy due to the rotational motion of the disk, that is by definition 1/2 of the moment of inertia multiplying the angular velocity w squared. Okay, we said that at the floor the block of mass m has potential energy equal to 0, because that point of the problem is the reference, right? The floor is the reference of the problem, so the potential energy is equal to 0 right there when the block hits the floor, and we write it down like that, right? Okay, we know that by definition the moment of inertia of the disk is 1/2 of the mass multiplying the radius square, and the relationship between the angular velocity and the linear velocity is v equal rw. This happens because the speed of the falling block must be equal to the tangential speed at the outer surface of the cylinder. So we have that relationship. Next, we are going to be straightforward to write the conservation of energy of the system to find whatever we want to calculate. Okay? So we use the conservation of the energy. We write the conservation of the energy like this. Energy, the total energy before is equal to the total energy after. Okay? The total energy before is equal to the total energy after. What is the total energy before on this situation? Is the kinetic energy plus the potential energy. Okay? Total energy before, let's write it down like this. Total energy before, total energy after. Total energy before is K1 plus U1. But what is K1? We know that is 0 because the block of mass m starts moving from rest, and its initial potential energy is equal to the mass multiplying the gravity multiplying the position. The same for the energy, the total energy after, right? On the second part is equal to K2 plus U2. But we know that on this part, the total energy, the kinetic is this, and the potential is this. Okay? So, we have 1/2 of the mass, velocity squared, plus 1/2 of the moment of inertia multiplying the angular velocity squared. Okay, guys, this is the kinetic energy before, and this is the potential energy after. So we have only on this situation the remaining energies before and after, like is written down right now. So we use the conservation of energy and we make these equations equal. So because this is equal to this, we can write mgh equal to 1/2 of the mass v squared plus 1/2 of the moment of inertia w squared. Okay, guys, we remember that the moment of inertia is this expression, and the velocity and the angular velocity are related with this expression. So I replace these two expressions into this equation. Okay? And I will get this. mgh equal to 1/2 of the mass v squared plus 1/2 of the moment of inertia, but the moment of inertia is 1/2 of the mass of the disk, radius of the disk squared, multiplying the velocity, angular velocity squared, but we know that angular velocity is equal to v is equal to w multiplying r. Then w is equal to, this is if v is equal to wr, then if I clear w from this equation, I will have that w is equal to v dividing r. Okay, so I replace that into this equation. Because this is w squared, I will have v multiply dividing r squared. Okay, easy. So I do some algebra here, then I will have mass gh 1/2 of the mass v squared plus 1/2 of the mass r squared. Okay, v squared r squared. Okay, I take the power on each expression, so v squared r squared. We can see that we can this r squared cancel with this one as well. They cancel each other because they are equal. Okay, finally I can write this expression like this. Mass hg equal to 1/2 of the mass v squared plus 1/2 of the mass. We remember that we canceled the radius of the disk, we will have this. Oh, give me a second, please. 1/2 multiplying 1/2 of the mass, okay, v squared. I can simplify this expression, so finally I will have something like this, mgh equal to. So I will do this. I will take this 1/2, this 1/2, this v square and this v square. Those terms are common on each part of the equation, so I will take common factor out, okay, like this, 1/2 of b squared multiplying m plus 1/2 of m. What I did, I took common factor out. That's what I did. So these two that is dividing on this part of the equation is gonna go to multiply on this part, and this whole part is multiplying here, is gonna go to divide on this part. Okay, when I do that, finally I will get something like this, 2mgh equal to v squared dividing m plus 1/2 of the mass. Okay, and finally I will have taking root square on both sides of the equation, taking root square here and taking root square here. Finally I will have that v is equal to root square of 2mgh dividing m plus n half. Okay, finally this is the velocity that the block has right before hitting the floor. This is the velocity that we are looking for. So the problem also says that we want to calculate the angular speed as well, right here, of the cylinder at the same moment, at the same time. So we know that the angular velocity is the relationship between the linear and the angular velocity is v equal wr, right? So the only thing we need to do here is we want to calculate this w, so w is gonna be v dividing r. Okay, so the angular velocity of the cylinder when the block right before the block hits the floor is gonna be w equal to this velocity, the velocity of the block, dividing the radius of the cylinder. Okay guys, this is the problem that we wanted to solve. Hopefully you like it. Please subscribe to my channel give me a thumb up. Thank you for watching me. See you in the next video. Bye.